I would like to sort of first kind of introduce, kind of the topic of quantum algorithms and kind of why we think quantum computers, might have speed up and somehow what we have to do to look for cases where we can have significant quantum speed up. And then I want to sort of talk about, briefly about a bunch of different classes of problems where we think we can do something, that may be interesting with quantum computers. So these will be sections on quantum algorithms for algebraic problems, quantum walk algorithms, quantum algorithms for simulating quantum mechanics, quantum algorithms for high-dimensional linear algebra, and then I'll talk just kind of very briefly at the end about sort of optimization and machine learning, which are actually areas that maybe I'm personally less optimistic about, but we'll get there. Okay, so let me start with kind of an introduction to sort of how I see the challenge of quantum algorithms and what it is we're trying to do and sort of where we need to look. There's this idea that somehow if we can build quantum computers, we can use them to solve some problems a lot faster than we could with ordinary classical computers. But, where does that come from? Like, why would we expect quantum computers to be more powerful or able to solve some problems faster? And, this is a kind of probably a deep and complicated question, but if I had to point to one thing, it's really the possibility in a quantum computation of having interference between different paths of the computation. There's this kind of wave-like, kind of nature of the computation, and our goal is to sort of arrange our quantum computation so that the paths that lead to the solution interfere constructively, and the paths that would lead to non-solutions interfere destructively. And so, when you have your final quantum state, it sort of is supported on the solutions. And, of course, wave phenomena are not somehow uniquely quantum mechanical. Like, we also have classical waves, but the thing that's special about these wave phenomena in quantum mechanics, and specifically in a quantum computational context, is that with a quantum computer, you can give a very efficient representation of very high dimensional interference phenomena. So if you arrange things in the right way, you can maybe have these kinds of interference phenomena lead to a solution in a way that you wouldn't be able to efficiently realize that solution with classical waves. Okay, so that's kind of the underlying picture that I have in mind. But now the question is really like, what are the problems that where you can hope to get speed up from this? And I think it's really kind of important to realize that, quantum computing is not somehow a magic bullet that just will solve any problem a lot faster. And in particular, quantum computing is not the same thing as just like exponential parallelism, where somehow you can try and superposition all these possibilities and somehow magically pick out, the thing that corresponds to a solution. So, you can think about this sort of like needle in a haystack problem. And I guess you have heard about Grover's algorithm, which is basically a quantum algorithm for solving this problem, somehow trying to find a needle in a stack of n pieces of hay. And somehow, what's achieved by this Grover algorithm, which is this quadratic speedup over a classical search, this ability to find this one thing out of n in only square root of n steps instead of the n that it would take classically, this is really the best that you can hope to do in some kind of black box model of the computation, right? So there's this lower bound of Bennett, Bernstein, Broussard, and Vazirani that shows that in a certain model that we call quantum query complexity, actually you need to query the input square root of n times with a quantum computer to find the thing that you're looking for. This is basically a consequence of the linearity of quantum mechanics. And so what this kind of tells us is that if we want to get significant speed up for this problem, but I think this is also true more generally, we need to have some structure that we can exploit, right? We can't just sort of view the problem as this kind of like completely unstructured thing and just sort of rely on the magic of quantum mechanics to find the thing that we're looking for. We can get some advantage from doing that kind of thing, this kind of speed up, this kind of quadratic advantage that you've seen from Grover's algorithm, but that's kind of the best you can do unless you sort of have more going on. So to me, kind of the key question about quantum algorithms is to understand, what are the kinds of problems that have some structure for which we'll be able to do this kind of high dimensional interference with a quantum computation in a way that gives us a big savings over what we could do classically. And this is not an easy question, and we definitely don't have anywhere near a complete understanding of, what this sort of structure, looks like generally, nor do we have that many examples of places where we can find this kind of structure. So this is kind of the thing to do in quantum algorithms, to find more examples of problems like this and to try to get a better kind of overall picture of what are the things that allow for significant quantum speedup. And at least in my view, if you want to sort of approach a problem with a quantum computer, you really should have a reason to think that it has that right kind of structure that's going to allow for things to be a lot faster, because it's definitely not a very generic thing. So I want to talk about another example that kind of relates to maybe some quantum algorithms that you've seen before that I think maybe makes this point even a little bit more vividly. And this has to do with Simon's problem and a related problem called the collision problem. So Simon's problem, I guess you've seen before. So let me just briefly recap what the problem is. So you've got this black box function that maps, let's say, strings of n bits to some range. It doesn't matter so much what this set is, but you have this promise that the values of this function are somehow very structured. They're structured so that if you look at what happens when you query the function on inputs, different inputs x, those inputs can be broken up into pairs. And some particular input x is going to be paired with another string, which is x XORed with some special string x bitwise. Right? So there's like this hidden string s. It's also an n-bit string. And the way you can find two inputs that evaluate to the same thing under this function is you take the one you started from and you XOR it with s. Right? So like the all zero string is paired with the string s, the string that's all zero is followed by a 1 is paired with the string that just flips the last bit of s, etc. Right? In general, x is paired in this special way with x XORed with s. Right? So this kind of hidden string is imposing a lot of structure on how this function looks. And our goal in this problem is to find s, and I think you've seen the quantum algorithm for this problem before, and maybe you've also heard about the classical hardness for this problem. So one way of trying to solve this problem classically is just to query the function at a bunch of randomly chosen places until you find a collision, right? If you find distinct inputs x and y such that f evaluates to the same thing on x and y, right? F of x equals f of y, then you can XOR together x and y, and that will tell you s. And by this thing called the birthday problem, this kind of standard problem in probability theory, you can show that you need about the square root of the total number of possible strings, in other words, the square root of 2 to the n, random queries before you expect to find such a collision. And this is basically an optimal strategy for this problem. So this is really like the best you can do. But quantum mechanically, you've seen that there's a one query algorithm that will basically learn one bit of information about s, right? It basically gives you kind of one linear equation that tells you something about s. And if you query a linear number of times, then you can determine what the string s is with good probability. So basically, the quantum query complexity of this problem is basically linear as compared with this exponential query complexity classically, right? So this is like an exponential savings of the quantum algorithm over the classical one. So I want to contrast this example that you've seen before with another example that maybe you haven't seen before, which is what's called the collision problem. So in the collision problem, you're also given such a function, and now you've got some promise. Let's say it's either a 1-to-1 function or a 2-to-1 function. And just to make things simple, like let's say your goal is just to determine which of these things is the case, right? So if it's a 2-to-1 function, that means it's a function that looks like what we have in Simon's problem, right? That if you look at the kind of possible inputs to the function, you can pair them up into pairs of inputs that evaluate to the same thing. So these black dots represent inputs, and these two inputs evaluate to the same thing. These two inputs evaluate to the same thing, etc. And then the other possibility is just that it's a 1-to-1 function, meaning like everywhere you evaluate it, you get a different output. And now you want to determine which of these things is the case. So you can show that quantum mechanically, you can solve this problem in n to the 1/3 queries. So n is this exponentially large thing. It's the number of possible bit strings. You can show using Grover's algorithm. It's a nice exercise to show how to do this. Maybe we don't have to go through the details, but you can show that with n to the 1/3 queries, you can solve this problem, but that's still exponentially many queries. And in fact, you can show that this is basically optimal. This is actually the best you can do, even with a quantum algorithm, right? So for this problem, there's no exponential quantum speedup. There's some polynomial quantum speedup that you can show that the best you can do classically is basically this birthday problem thing. It's like the square root of n. So there's a little bit of quantum speedup, but it's not exponential quantum speedup. Okay, so what's going on here? So we also had this 2-to-1 kind of structure in Simon's problem, but in Simon's problem there was much more structure because these things were paired up in a way that had to do with kind of the bit representations of these values, right? X was paired with, X XORed with S. So that there was like a lot more structure in the Simon's problem that the quantum algorithm is taking advantage of in order to be able to do things much faster, right? If you had this collision problem and you were promised that in the 2-to-1 case, the function had the structure of the Simon problem, then you could actually solve this problem very efficiently in time, polylog capital N, right? Polynomial in little n. So there's what's going on is that there's like a lot more structure, and with this additional structure, we can get significant quantum speed up. And so this is basically what we sort of want to understand in general, right? So the collision problem doesn't have enough structure to give us a fast quantum algorithm, but in Simon's problem, we have some particular structure that we can latch onto that allows us to, with this kind of Hadamard transform on some particular kinds of quantum states, solve the problem a lot faster, and this gives us exponential speed up. So, what we want to understand in general is like, what are the problems that have fast quantum algorithms, but not fast classical algorithms? And kind of more broadly, what are the kinds of structures? So for example, the structure that's here in Simon's problem is a structure that kind of enables significant quantum speed up. But, what are the other structures that enable a significant quantum speed up? And there are some others that are known, but there's definitely not a very good kind of overall understanding of this question. And, of course, it's not, I don't want to completely discount the possibility of having something interesting happen with less than exponential quantum speedup. I think it's also interesting to think about when we can get polynomial quantum speedup, and when that's the case, how much polynomial speedup is possible. So that's also a thing that's, definitely worth studying. But, we're definitely going to get the most bang for our buck when we try to build a quantum computer if we can really get exponential quantum speedup. Okay, great. All right, so now what I would like to do is sort of talk about a bunch of different, kinds of quantum algorithms, some sort of like families of quantum algorithms, and just talk a little bit about what's known, and kind of where things might be headed in the future. Okay, so let's start out by talking about algebraic problems, which, many of these quantum algorithms for algebraic problems have to do with kind of identifying hidden symmetries, right? So the Simon problem, can be thought of as an instance of this more general family of problems that have to do with identifying some sort of hidden symmetry. Shor's algorithm for discrete log and also the factoring algorithm can be seen as doing something, very similar to this. And there's a kind of a general class of problems that has been studied called the hidden subgroup problem that kind of formalizes this idea of identifying hidden symmetries. So in the hidden subgroup problem, you're given some group, so you know what this group is, and then you're given the ability to query some black box function that maps elements of the group to some range, and you've got a promise about the structure of the function. So this is a promise that, maybe in some cases could be helpful for getting significant quantum speedup. The promise is that the function basically like respects the symmetry of this group in some sense, specifically that it's constant on cosets of some subgroup of the group. So there's some unknown subgroup H of G, and it's distinct on different cosets. And so you can sort of cast the Simon problem in this sense for some particular group, but you can do this much more generally for other groups. And so you have this picture where you've got this function that takes one value on, let's say, the elements of the subgroup, and then different values, different constant values on different cosets of that subgroup. And then your goal is to figure out basically what the subgroup is. And there's an approach to this problem, which is the approach that's used in the algorithm for Simon's problem that you've seen, which is sometimes called the standard method. So the idea of this approach is that you take a uniform superposition over the elements of the group, and then you query the function in superposition on all of those elements, and you basically like discard the information about which function value you have. That basically is going to project you onto a uniform superposition over the elements in one of these cosets. And you're not going to know which coset you get because you're just going to get some function value. These function values don't really mean anything to you, but you're going to get one of these coset states. So this pictorially, this is like a uniform superposition over the elements within one of these cosets. Okay, so this problem can be considered for all kinds of groups. And if we think about the special case where the group is abelian, where this group G is abelian, then there are lots of applications of quantum algorithms that are known in that setting. So you can think about the discrete log algorithm as an instance of that kind of a problem. You can think about factoring in this sense, but now here the group really should be kind of formally infinite. There's maybe some question about how you sort of like handle that with a digital computer, but you can. And then there's a bunch of other sort of like number theoretic kinds of problems that can be cast in terms of problems that have to do with finding hidden subgroups of abelian groups. Like, for example, problems relating to counting points on certain kinds of algebraic curves, or various kinds of problems in number theory, some of which relate to cryptography. So there's a bunch of kinds of problems that we can sort of approach in this way. Another thing that can be put in this framework is, kind of the case where it comes from the case where the group is non-abelian, so where the elements of the group do not commute. A lot less is known about this case. So in this case, you can show that polynomially many queries to the black box suffice. So these coset states can be used in principle to find what the hidden subgroup is with, only polynomially many queries to the black box. But whether there's an efficient quantum algorithm that can sort of, process those states with only polynomial running time to determine what the hidden subgroup is unclear in general. So there are some special cases where it's known how to do that. But on the other hand, there are some hidden subgroup problems that, if we could solve them, would have really, really interesting applications, but for which we don't know how to solve them efficiently. And probably the kind of most exciting of these is, has to do with what's called the dihedral group, for which, if we had a solution of the hidden subgroup problem that kind of follows the framework that I sketched, we could actually give quantum algorithms for lattice problems, which are the leading candidates for quantum secure cryptosystems, right? So the kind of fact that Shor's algorithm breaks RSA and Diffie-Hellman and other kinds of public key cryptography has led to this interest in finding cryptosystems that would resist quantum attacks. The leading candidates are based on these lattice problems, which there would be attacks on if we had quantum algorithms for this dihedral hidden subgroup problem, but no such quantum algorithms are known. And in fact, no efficient quantum algorithms for these problems are currently known. So, that's one of the reasons people have been interested in this hidden subgroup problem. I would say progress in this direction has kind of stalled in recent years. There are some kind of hardness results about the kinds of processing you would have to do on these states to recover the hidden subgroup. These results are kind of far from ruling out the possibility of an efficient quantum algorithm, but we also don't have a lot of great ideas for how to move forward in terms of finding better. So this is I think it would be a nice area to make some progress on, but not one where there has been much progress recently. Okay, so that's just a very quick overview of this kind of area, but, in light of the time, let me maybe move on and tell you about some kind of other areas in quantum algorithms. And I'd like to talk a little bit next about this idea of a quantum walk on a graph. So the idea of a quantum walk has to do with trying to come up with a quantum mechanical analog of a random walk or a Markov process. Random walks or Markov processes are really useful tools for classical algorithms. And so it's natural to imagine that if we could come up with quantum analogs of them, we could do interesting things with quantum computers. And so that's the reason that people have spent a lot of time studying what quantum walks might be useful for in a quantum context. So the kind of idea of defining this notion of a quantum walk on a graph is basically, to think about replacing the probabilities that characterize the dynamics of a random process, like a Markov chain, by quantum amplitudes. And so you can get an analogous but totally different process. And since now you can have interference phenomena occurring in the quantum walk, you can have radically different behavior. So for example, here's a picture of what the classical random walk distribution of a classical random walk on a line might look like. If you start at the origin and you sort of randomly decide whether to move left or right, you get this kind of Gaussian sort of spreading of the probability. And quantum mechanically, you have some interference that takes place that allows you to move much faster, further away from where you started, and you have this more complicated looking distribution. And so the kind of hope in this area has been to try to use these quantum mechanical processes on graphs to find faster quantum algorithm. So let me maybe mention a few of the things that are known about what these quantum algorithms can do. To do that, let me maybe first formulate a little bit more precisely what I mean by the quantum walk. And there's actually different ways that you can define a quantum walk. Two natural ways involve doing it with a process that sort of evolves continuously in time, or one that evolves with discrete steps in time. And it's actually, in some ways, a little bit simpler to think about the one where the walk evolves continuously in time. So let me briefly introduce that. So imagine that we have a graph. So we have vertices, and then we have edges that join the vertices that describe sort of things that are next to each other in the graph. And we can characterize that graph by a matrix called the adjacency matrix, where we have entries that are 0 and 1, where the ones correspond to vertices that are adjacent. So for example, vertices 1 and 2 are adjacent, and that's why there's a 1 in the 1, 2 entry of this matrix. We can also define another related matrix called the Laplacian of the graph, which is basically the matrix where we have it's like minus this matrix. So we have minus ones in the off-diagonal entries corresponding to the edges of the graph. And then on the diagonal, we put the degree of the vertex, like the number of edges coming out. And so like vertex 1 has 2 edges coming out, so we put a 2 there. So this is a kind of you can think about this as kind of like a discrete approximation of kind of the second derivative operator on the graph. And now if you want to define a random walk, a continuous time random walk on the graph, you can do it by saying, okay, we've got a vector of probabilities. PV of t is the probability of being at vertex v at time t. And then consider this differential equation. The kind of derivative of p is the Laplacian acting on p. So this is going to describe some kind of diffusion of the probabilities on the graph. But quantum mechanically, imagine that instead of sort of trying to capture these probabilities, you want to understand how these amplitudes evolve. So you've got an amplitude AV of t to be at vertex v at time t. And if you just put an I into this equation, right? So this equation is just the same thing, except we put an I in front of the derivative, then this is going to describe unitary dynamics on the graph, where now you're going to have interference, as you do in quantum mechanical processes. And so it's going to be in some ways analogous to this classical process, like the amplitudes will evolve locally on the graph. They move around locally, but now we have the possibility of interference, and the dynamics can be very different. Okay, and yeah, there are maybe different ways of defining this that all kind of make sense quantum mechanically, but maybe let's not worry about it. Okay, so one example of kind of a significant quantum speedup that was discovered using this idea of a quantum walk on a graph, came from this continuous time walk model, and it works as follows. So imagine that you construct a graph by taking two binary trees, and then you join the leaves of the binary tree on the left with the leaves of the binary tree on the right by sort of a random cycle that alternates between the left side and the right side. So you go back and forth until every vertex here has two neighbors to the right and every vertex here has two neighbors to the left. So then when you do that, you have this kind of mess where almost every vertex in this graph has three neighbors, except this one that I labeled in has two, and the one that's labeled out has two. And now our goal is to sort of like think about this as sort of like a maze where we start it in and we want to find our way to out. And you can kind of formalize this by a black box model where the vertices have labels, and you have a function you can call that if you supply it with a label, it will give you the labels of the adjacent vertices, right? So that's like a way you can sort of explore this graph or walk around in this maze, by sort of starting at some vertex whose name and then querying the black box to find your way to other places in the graph, right? So suppose you're given the label of this in vertex, and your goal is to find the label of the out vertex. Well, quantum mechanically, what you can do is you can run a quantum walk, this kind of continuous time quantum walk that I introduced on the previous slide, starting from the in vertex. And what you will find is that it stays within a simple invariant subspace of the full Hilbert space that this quantum process explores. It stays within these uniform superpositions of our vertices in a given column of this graph at a certain distance from the in vertex. And because of this, you can show, there's a calculation you have to do, but you can show that the walk will reach this out vertex in a small amount of time, like in an amount of time that grows something like the height of this tree. Whereas the number of vertices in the graph is exponentially large as a function of that parameter. So what that tells us is that this quantum walk will actually basically reach this out vertex, and you can use it to solve this computational problem of finding the label of the out vertex. But you can also prove that a classical process, a classical random walk, but also actually any classical process that any classical algorithm you can try to run will not be able to, in polynomial time, find the label of the out vertex. So this is an example of, a quantum walk getting an exponential speed up over what can be done by a classical algorithm for a kind of a toy problem. You can think about this as kind of like an analog of Simon's problem, but for quantum walks. So this is kind of encouraging because it says that this quantum walk idea can be really computationally powerful. There are also, other things that we can do with quantum walks, and there's also other kinds of quantum walks that we can define. And for some purposes, it's useful to have a notion of a quantum walk that takes discrete steps in time rather than being defined as a continuous time process. This sort of, for technical reasons, is a little bit harder to define. Actually, maybe I can just sort of explain why this is harder to define. So like, imagine you wanted to define a discrete time process that moved you in superposition just on a path. So then you would like to move from, let's say, the vertex X to a superposition of the two adjoining vertices. This would be a natural way to sort of write that down. But this is actually not a unitary process. Like, you can show that if you would do this, it would evolve orthogonal states to non-orthogonal states. So that's actually not a valid quantum process. Like, it's not a thing you could do on your quantum computer. And it turns out that there's kind of a way around this, which has to do with this notion of introducing what are sometimes called coins, basically another register that remembers a little bit of information about where the walk was in the past, kind of remembers the previous position. And this remembering will sort of reduce the potential for interference a bit, but only a bit. And so, that won't be a major problem for getting kind of significant interference that can lead to computational speed up with these processes. So there's a kind of a process that you can, or a procedure you can go through to define such a discrete time quantum walk, which is kind of outlined here kind of starting from any classical Markov chain. Maybe in the interest of time, I won't try to kind of explain all of the details, but maybe you can just trust me that it's possible to define a unitary operator kind of corresponding to an underlying Markov chain that gives you some kind of quantum analog of that process. And these discrete time quantum walks, are also useful for getting some quantum speedups. One kind of framework where they're useful is this idea of quantum walk search, which is a way of solving some kind of search problems where the way you explore the different states that you're searching over, it comes from some given graph. So let me define this setup. So imagine you're given some graph. So you've got, vertices and edges. Some subset of the vertices are considered marked, and your goal is to find one of these marked vertices. Or you could think about the decision problem of figuring out whether there are any marked vertices. So that's this question of just determining whether the marked set is empty. And now there's a natural way of doing this, which is basically just to walk around on the graph at random, right? So take some random walk on the graph until you happen to reach a marked vertex. Start from maybe a uniformly random vertex of the graph and then walk around at random until you find a marked vertex. And if you follow that strategy, then the time that it will take to hit a marked vertex basically goes like 1 over delta times epsilon, where delta is a parameter that basically captures how fast you move around the graph, sort of how rapidly you get lost if you just start walking around at random. Formally, it's this thing called the spectral gap of the walk. And epsilon is just a fraction of marked vertices. So like the more vertices are marked, the easier it's going to be the easier it will be to tell the case where some vertex is marked from the case where no vertex is marked. Lots of marked vertices makes it easier to find one. So this is the time that it will take to hit a marked vertex. And you can show that quantum mechanically, if you consider this discrete time quantum walk that was introduced on the previous slide, you can construct a process that can be used to find a marked vertex or tell whether there is a marked vertex quadratically faster. Sort of some of the details about how this is done are mentioned here. Strictly speaking, you define sort of this discrete time quantum walk corresponding to kind of a slightly changed process where what you do is you stay at a marked vertex if you reach one. This is this notion of an absorbing walk. And then what we're going to do is not just walk around and see where we go, but we're actually going to run a process called quantum phase estimation to get some information about what the walk is doing. But, if you sort of sort out these technical details, basically the bottom line is that we can sort of like determine whether there's a marked vertex in the graph kind of quadratically faster than we would be able to find one by this classical process that walks around until it hits one. And this idea of quantum walk search is sort of a primitive that you can think of as generalizing the Grover search algorithm. And it can be applied in some cases where you can't kind of directly use Grover search to get quantum speedup. So, you can sort of think about the unstructured search problem as coming from the case where you have like the complete graph and you've just got, let's say if you could have only one out of the n items could be marked. So this fraction of marked vertices could be 1 over n. The spectral gap of this graph is really big. It's basically constant. And so if you plug into these formulas that I gave on the previous slide, you find this kind of quadratic speedup that you get from Grover's algorithm. But there are other problems for which you can get quantum speedup from this framework that Grover's algorithm sort of wouldn't give you. And the most famous of these, and the one that kind of originally motivated this framework, is something called the element distinctness problem, which is basically a problem having to do with finding some kind of collisions. You want to know for this function, is there a distinct pair of items, x and y, for which f of x equals f of y? And yeah, maybe in light of the time, I won't try to kind of go through the details about how this works in this framework, but I'll just say that, classically, basically, sort of nothing you can do better for this problem than just to query the function on all the possible inputs. But quantumly, there's a way of walking on a certain graph called the Hamming graph, for which you can get some speed up. And you can get, what you can show is that you can get, you can find such a collision, or rather you can tell whether there is such a collision with a complexity that goes like n to the 2/3. So this is an example of a problem with polynomial quantum speedup, not exponential quantum speedup, but one for which there's some structure that you can use to get some quantum speedup. And more generally, you can apply this idea of quantum walk search to get speedups for other kinds of problems. Okay, so that's a kind of very quick introduction to some of the things that you can do with quantum walk algorithms. In light of the time, I think I'm going to move on, and I'm going to talk a little bit about Hamiltonian simulation. Okay, so Hamiltonian simulation is really one of the major potential applications of quantum computers. I think it's probably the one that's sort of likely to bear fruit the soonest, and I don't know, maybe to bear the tastiest fruit, because it's it's a probably unlike, let's say, factoring, we really want to solve. We really want to understand the behavior of quantum mechanical systems. And it's a problem that really is hard as well for classical computers. So, maybe you've seen before this kind of quote from Feynman, where he sort of identified this problem of simulating quantum mechanics as a really natural thing to do with a quantum mechanical computer. This was kind of the problem that led him and others to sort of first think about this idea of a quantum computer. And so, this problem, as we sort of now understand it, is basically the following. So we've got a description of a quantum mechanical system specified in terms of an operator called its Hamiltonian. It's like a Hermitian operator that basically tells you about the energy levels of the system and will define the dynamics of the system, how it will evolve in time. And then you're given an amount of time you would like to evolve for. You're also given an initial state of the system in the memory of your quantum computer, and your goal is to figure out what the dynamics of that system would do. So what the quantum state would be, at this final time t. And, it's maybe enough to do that approximately up to some error tolerance epsilon. And this is the goal here, I should say, is not to, give a kind of a complete description of what this state is, but rather to produce a copy of this state in the memory of your quantum computer. And then that's something that you could use, you could perform measurements on to learn things about the state of the quantum system. I'm going to sort of not think about that part of the problem and just think about the problem of simulating the dynamics in this sense of like producing the quantum state. Okay. So, this problem, as I'm describing it, is an inherently quantum mechanical problem. We can't hope to, even represent general quantum states efficiently on a classical computer. And, the quantum computer is somehow not giving you that complete description. It's just giving you this quantum mechanical representation. But there is a sense in which this is a problem that, a quantum computer can solve and a classical computer, cannot, at least if there's anything that a quantum computer can do that's not simulatable by a classical computer. So we say that this is an example of what's called a B2P complete problem, which basically means that it characterizes the difficulty of what quantum computers can do. So like any problem that can be solved efficiently by a quantum computer, for example, factoring, could be cast as an instance of this Hamiltonian simulation problem.